Hello everyone and welcome back to this online NPTEL course on aquatic geochemistry. We have been discussing stable water isotopes since our last few lectures, and in this particular lecture also we will be discussing about the stable water isotopes, what causes its variation and how do we use this kind of information from natural samples to understand paleo temperature, mixing in the oceans and things like that. So, let us directly move into the factors that controls the isotopic composition of precipitation. In our last lecture, we discussed about the Rayleigh fractionation and the way the isotopes vary, the composition varies. Now, with respect to the stable water isotopes, we have found out for precipitation there are majorly 6 contributing factors. The first factor is temperature. Now, what does temperature control? Temperature has an effect on the isotopic composition of the precipitation, mainly because it controls the amount of water that can be stored or held in a given air mass. Okay. So, what is the surrounding temperature? What is the surrounding air temperature? Okay. What is the average weather temperature? That will decide how much moisture can that particular air mass hold. If you are staying in a very hot, arid, dry region, the air mass can go on holding a lot of moisture as compared to a very cold, dense, heavy air, which beyond a certain point will not be able to hold the moisture and will therefore start precipitation. So, due to this difference that changes mainly with the ambient temperature of that particular region, we see strong correlation of the delta 18O values of precipitation, that is rainfall, with the temperature of the surrounding region. So, here in this plot you will see in the x axis there is mean annual air temperature, this is annual average, and this is the delta 18O of precipitation of rainfall that has been measured with respect to V snow. Okay. So, V snow, and you see that for the variation is very large. So, this is in the polar regions and this is near to the tropics, right. So, we see that near the in areas which is more colder regions and all, the relationships are pretty good and linear. What happens is there is more effect of other factors in the hotter regions, in the more tropical areas, and in this regions there can be other factors that that is active to cause such variations. Okay. But in most of the higher latitudes, in most of the higher altitudes and in the colder areas of the planet, we see that there is a very good correlation with the temperature and the delta 18O values. Okay. And why do we see these kind of temperature? It has to do with the fractionation of the isotopes. Okay. So, the values of 1000 ln alpha LV, that means the difference between the delta values for H and O, it varies strongly with the surface temperature, but the ratio does not vary a lot. Okay. So, the ratio of the hydrogen and the ratio of the oxygen, they do not vary much. So, therefore, they have a nearly constant value of 8.1. Okay. So, this is why we have the global meteoric water line. It is because of this particular factor that hydrogen isotopes and oxygen isotopes, although they vary with the temperature, but the ratio of the two remains constant, and that dominantly is controlled by the fraction of the vapor that is remaining in the air mass. So, this is controlled by the humidity, this is this is controlled by the temperature of the region. So, this is why we see such correlations with the delta 18O and the delta D values and with the water isotopes and the temperature value. Okay. And always remember, this alpha value is also very much dependent on the temperature. So, therefore, due to these reasons we see a strong effect of temperature on the composition of the precipitation. Okay. Now, from a lot of data, as we have, as I have shown a a couple of lectures back, that we have many hundreds of locations under the GNIP program that is monitored by the International Agency of Atomic Energy, and they routinely do this checkings and have a huge data set. Now, combining all these data sets, it is found out we have now got a empirical relationship. So, the delta 18O is equal to 0.69 times the temperature, average temperature of the region, minus 13.6, and with the delta D the relationship is 5.6 into average temperature of the region minus 100. And this this ratio of the delta 18O and the changing temperature remains very constant at 0.69 at the higher latitudes. This remains a very strong correlation. So, any change in the delta T, so any change in temperature, if you want to calculate, if you do not have samples, but you can have a rough estimation of the delta 18O by just using this empirical relationship, and this seems to be working very fine for the higher latitudes as compared to near the equator and near the tropics. Okay. So, this helps us in understanding both the temperature, specifically when we are using stable water isotopes in our paleo temperature studies. The second controlling factor is the distance or the continentality effect. Now, I have already explained this a little bit in the Rayleigh fractionation when I was explaining the Rayleigh fractionation. So, what is happening as the air mass is moving on top of the the continents, and you see through the mountains and all that finally gives to the 0 degree to 90 degree. As it is moving inland, as the clouds are moving inland, there are more and more cycles of precipitation events. Okay. There are more and more cycles of precipitation events. So, what happens is, as soon as the air mass moves away from the coastal areas, it starts getting depleted more and more. So, there is less of the initial fraction of the vapor that got transferred from the oceans. Yes, there will be some local vapor that is contributing again, but in case of a phenomena, something like monsoon and all that, the contribution of this kind of precipitation, the contribution of this kind of evaporation to the precipitation is very negligible as compared to the vapor that is coming from ocean sources. So, therefore, we see that as it is moving more and more into the continent, we are getting depleted delta 18O and delta D values. So, the 18O is getting less and less, and the 16 oxygen is getting enriched in the water. Okay. So, therefore, we are seeing this kind of variation. The continentality effect is also associated with a number of other physical controls on F, and the most notable among them is the temperature, because the temperature is also changing from 0 to 90 degree. Okay. So, this temperature difference is maximum when we consider the source of moisture, which is often near the equator or near the tropics, and the point of precipitation, which can be far inland, and therefore, there is a huge difference in temperature. And it is also, the delta T is also tied to the seasons, whether it is an ongoing summer season, whether it is an ongoing winter season. It is due to these differences with the temperature and with the rainfall cycles that we see a stronger continentality effect during the colder months as compared to the summer months. Okay. Due to the less temperature and more fractionation at lower temperature, this kind of continentality effect is greater during the colder months as compared to the summer months. Okay. So, first it was temperature. So, temperature was mostly related to how much air, how much fraction of vapor the air mass is holding. Second of all is the continentality effect, which is like how much rain out is happening as we move into the continent, and as we are progressing more and more into the continent, the temperature is also changing, it is getting lowered, and if it is a summer season or a winter season, the continentality effect can have a more or less impact on the precipitation composition. The third factor that affects the precipitation composition is therefore also the latitude, right, because here we are also moving across the latitude. So, again it is very related. So, the degree of rain out of air masses increase as we are moving across the latitude, and the temperature definitely decreases with the latitude. As we are going towards more and more higher latitudes, the temperature is definitely decreasing. So, the overall impact we are seeing that we are seeing a more depleted delta ET nO or more negative delta ET nO and delta D values at the higher latitudes. Okay. Now, we have collected a lot of data from variety of latitudes, and therefore, now we have an empirical relationship where we expect that 0.5 parts per mil will decrease with the increase in latitude, with the increase in per degree of latitude. So, between 10 degree and 20 degree, you expect how much? At least 5 parts per mil difference. Okay. So, per degree latitude you expect that it is going to decrease by 0.5 parts per mil, and this is only coming from the latitude. Another extremely important factor is the altitude. So, even at lower latitudes we have many places which is higher altitude. For example, you have the Western Ghats, you have the Himalayas, which is latitude wise it is very low, but altitude is like 7,000-8,000 meters above the sea level. So, even that altitude can cause a huge amount of differentiation in the composition of precipitation, and that is again related to temperature. So, at higher altitudes the air mass gets cold and it is holding less water, and the effect of Rayleigh fractionation therefore increases. So, what we see is that at higher elevation we have more and more negative values as compared to the more lower altitude. So, as we are going up the mountain, the values of delta ET nO in the precipitation is going to decrease, it is going to go more negative. So, if we are at 1000 meters above sea level, your value expected to be is around minus 3 parts per mil. If you are there at 6000 meters above the sea level, you can expect something around minus 15, minus 2, minus 20 parts per mil the delta ET nO value, and this is again coming just from the altitude effect that is again controlled by the temperature. Okay. Now, again from entire thousands of data sets, this paper by Poage and Chamberlain in 2001 they compiled, and they concluded that there is a gradient of 0.26 per mil for per 100 meter of increase. Okay. So, if you are increasing by 100 meters, your delta ET nO value will decrease by 0.26 parts per mil. It is a negative, so it will decrease. So, with the increase in altitude, there will be the decrease in the delta 18O isotope composition. And this is, this characterizes this kind of correlation, this kind of relation. Okay. It characterizes most places in the world and up to 5000 meter. Above 5000 meter, this correlation might have a different value. It will be there, but the value may be a little different. Okay. So, this is about the altitude effect, and this is why in the in Himalayan glaciers and all that, we have very negative values. Okay. It is not to do with the continentality effect, it of course has to do a little bit, everything will play a part, but the altitude is huge. Its altitude is a very big player, and of course, the contributing factors like temperature, the other contributing factors like the source of the moisture is also going to be very important, but this empirical relationship with the altitude is extremely important, because we see it as we are going to climb the mountain. Okay. As we are going to collect the samples from the different heights, we are going to see this kind of relationship. A mount effect, and this is the most important factor in the tropical regions. Okay. In the tropical and the subequatorial and the equatorial regions, the mount effect is the most dominant effect among all the other that we have seen so far. And what does it mean? The mount effect means that with more and more rainfall, as it is getting removed, the delta 18O value is getting negative. So, what is happening in the first rainfall? Okay, the first rainfall that was happening, okay, the first few millimeters of rainfall, they had a value of -2 parts per mil, consider. But as it is raining more and more heavily in the same location, so here we are considering one particular location, but with very high rainfall. So, the rainfall is going to get very high. So, in that particular location, if the rainfall amount was low, we have a value, but if we had a very high, like 4 times higher that rainfall, then we see that the rainfall value is very less, the delta 18O value of that rainfall is very less. And why is that? Because as it is raining, the 18 oxygen is continuously getting removed, preferably with the rainfall. So, as the vapor, which is remaining vapor, is getting more and more depleted with the 18 oxygen. So, the last rainfall that is happening, which is like after 300 meters. So, the later rainfall is going to be very depleted in delta 18O composition. It is going to be very depleted in 18 oxygen composition, and therefore, the delta 18O value will automatically become more and more negative. So, it is like the more rain out effect, but not with different latitudes, not with the continental distance, but at the same location only with the amount. So, at a particular location you are having a lot of rainfall. Due to this heavy rainfall, what is happening? Delta 18O is more and more getting removed as there is more rainfall events happening. So, the final rainfall events, which is having a huge amount, now the total cumulative amount has increased, then you see that that rainfall will be very negative. Okay. So, the 18 oxygen composition of that particular rainfall will be very low, it will be a highly negative value. So, this particular phenomena or observation is called the amount effect, and it is mostly seen in the tropical regions and the subequatorial regions, because here the amount is more, here you receive a lot of rainfall as compared to the more temperate regions where we do not expect a lot of rainfall to happen. And of course, in the poles it is always just snowfall, but there is a less chance of fractionation, because there already the vapor mass is now remaining with more of 16 oxygen and extremely less of 18 oxygen. So, almost the precipitation fractionation is not so not so significant. Therefore, the tropics, where you saw the latitude will not play a very big difference. The altitude will not have a very significant difference apart from mountain chains. The continentality effect will be very low because most of the ocean coastal regions lie in the tropical and equatorial regions, and also the temperature is low. So, therefore, the temperature related fractionation will be low in the tropical regions. So, what will be the most important effect? It is this amount effect. So, in the tropics the amount effect is more and more important. So, this is just another data set which is from Israel, published by Barr and Matthews in 2003. So, and also this this kind of effect you will see in the months of rainy season as compared to rain happening in any other season. So, when you have a monsoon, there is continuous rain out effects. So, those data will have significantly lower values as compared to if rainfall is suddenly happening as a single event in some kind of dry season, like say suppose in February it is raining and you check the composition, you will see a much more enriched composition as compared to the rainfall that happened in sometime in August or September, which is like in the middle of the monsoon season, that is the entire air mass is seen a lot of rain out. Okay. Seasonal effects. Now, all the factors that we have discussed so far, that is temperature, altitude, latitude, distance from the coastal areas, that is the continentality effect, the amount effect, everything influences the seasonal effect. How much difference are we going to see in between the seasons? And most of it is related to the temperature and the altitude. And of course, if it is near to the coastal ocean or if it is near to the tropics and all that, then the amount effect is also very important. So, this we are seeing that in winter the values are more in the negative region because of direct influence of temperature. In summer the values are shifted more towards the positive 18O and delta D values. Okay. And this is again very strongly observed all over the world, this kind of seasonal shifting. Now, moving to other applications, for instance delta 18O is hugely applied for understanding various various applications. That is mainly because water itself is itself composed of oxygen and hydrogen, and if we are mostly tracking the sources of water, delta 18O is of immense immense importance. And here you see there is a plot of delta 18O versus delta D, and there is a difference observed with the local meteoric water, that is the local rainfall, with the geothermal water. So, what is happening here is that the local meteoric water, wherever is rainfall is happening, it goes inside the cracks, it will go inside the soil, and there will be some heating source, the geothermal source. So, some kind of geothermal source is there. So, what will happen, this water will again come up through some weak point, that will rupture, and there will be a spring or some kind of exposure which will leak out this water. So, this water we term it as geothermal water, that is either the groundwater or the rainfall, it gets heated up. It gets heated up due to a geothermal source, that is some source that is coming from inside the earth. So, that may be some hot lava source or something very close to a magma chamber. So, the water gets very heated and it will it will seek a point of weakness. So, it will see any rupture point, it will see a point where it can get released, because there will be a mixture of vapor and hot water. Okay. So, the water will come out, and this water is called geothermal water. And I think if you are living in, if you have visited somewhere in the mountain areas, especially in the Himalayas, you will see there are a lot of hot springs. And there are a lot of hot springs, and these are natural springs. That means they they are very close to some sort of heat source inside the earth's crust, maybe due to some magma chamber, or or due to tectonic friction, some kind of tectonic activity which is causing the water to increase its temperature, very hot water, close to its boiling point. In fact, it is boiling water basically. So, there will be a lot of pressure due to a lot of vapor formation, and this water often will just get released in whatever weak point it finds. So, when we do analysis of this kind of hot spring water, that is geothermal water and all, we find that it is very enriched in the delta 18O axis as compared to the delta D axis. So, here you see that this is a plot of geothermal water from different regions like Virakel, in Iceland. So, there is a different regions, okay. And the meteoric water, that is the local precipitation, has this kind of value and strongly falling on the global meteoric water line. But when you plot the geothermal water seems to be shifted along the, delta 18O axis, along the x axis. So, question comes, why is this shift only in the 18O axis and not in the delta D axis? It is because when it is getting heated, very high temperatures, then interactions, reactions, exchange reactions start forming with the igneous rocks. And during this kind of reaction, the 18 oxygen of the water gets exchanged with the oxygen concentration in the minerals, in the rocks. Okay. Now, minerals, rocks, they are more stable phases, right, they are very stable phases. So, they will have more 18 oxygen concentration as compared to 16 oxygen. So, when the water is interacting with the rocks, it will exchange its 18 oxygen, it will become more enriched with 18 oxygen as compared to the meteoric water. So, therefore, geothermal water has more positive delta 18O values as compared to the rainfall, as compared to the original rainfall from which it is being formed. And the lack of shift in the hydrogen axis is because igneous rocks or carbonates, they almost lack any hydrogen. So, therefore, in carbonates and igneous rock, due to the absence of hydrogen, there is not any significant exchange between the hydrogen isotopes of water and the interacting minerals and rocks. So, the hydrogen isotopes see no such fractionation or exchange, but the 18 oxygen undergoes a lot of exchange, due to which we see such values for geothermal water as compared to the local meteoric water line. Now, an important, very important application of delta 18O and delta D is its application as a source tracer. What do I mean by a source tracer? Okay. So, when we are looking at in an aquatic system, say I am looking at a river. Okay. So, this is the river. Okay. I want to understand how much of the river water is coming from precipitation, how much of this river water is coming from maybe groundwater, how much of this river water is coming, if it is coming from snow melt, okay, if there is any snow melt, or if it is a glacier source, then how much is coming from the glacier ice. Okay. So, these are my components, these are my end members that is supplying the water to the river. Okay. All the water that is coming in the river is coming from these kind of source end members. It is not only river, for instance groundwater, that also is coming from precipitation, or if it is in the higher altitudes and latitudes, it is also coming from snow melt or ice melt from the glaciers. Okay. So, when we are trying to understand, okay, where is this groundwater that I am drinking coming from, or where is the river that I am using its water from is sourced from, then I want to do, to maybe to understand whose contribution is more, whose contribution is less, how are these contributions going to vary in the future, what threats do we see, with climate change, with changing anthropogenic, land use, and with the, increasing interventions, such as over extraction or changing the over extracting the groundwater. So, how are we seeing the changes impact the river flow, or how are we seeing the changes in the groundwater? Okay. So, for that kind of understanding, for that kind of appreciation of the sources, we need to do something called the source tracing or called source apportionment. Now, when we are going to do source apportionment, what we need to find extremely important is something called traces. Traces that vary with the different sources. Traces that vary with the different sources. As we have discussed in the lecture that was related to mixing theory, that only if the end members have different values and have different values such that we are able to separate them, will we able to separate them. Otherwise, it is extremely difficult with overlapping signatures to separate them, right. So, for being a tracer, first thing it has to have is, it has to have different end member compositions, okay. End member compositions should be non-overlapping. As second of all, it has to be conservative. Extremely important consideration when you consider what to use as a tracer. What do I mean by a conservative tracer? A conservative tracer is a tracer that does not change its value after or when I am mixing. So, if I am mixing snow melt, if I am mixing precipitation, the mixed water is just a result of the fractional contributions. It is not due to any other physical, chemical, biological interactions. Okay. So, then only if I know that the delta 18O of the mix is due to the delta 18O of the delta 18O of A into fraction of A plus delta 18O of B into fraction of B. Only this factor is controlling my delta 18O of mix. No other reactions, no other exchanges are going to contribute to my delta 18O mix values. Only then will I be able to calculate my FA and FB, that is my fractional contributions from source end member A and from source end member B. But if I do not have that kind of conservative signature, it is extremely difficult to see which is the source. Okay. In this regard, delta 18O is extremely good conservative tracer. That means they do not interact with the biological, with the other processes at low temperatures. At low temperatures, at earth's surface temperatures, okay, that is around something around 15 to 20 degrees centigrade, they do not undergo a lot of chemical reactions, they do not react as they are moving in the river. The delta 18O and the delta D, they are bound with the water molecules. Only if you are reaching a temperature such as that in the geothermal system, only then you will see the changes, otherwise it will not change in a low temperature environment. In a low temperature environment, there will not be any kind of chemical interactions. Similarly, we expect that the physical processes that could alter the delta 18 or delta D values is accountable. That means, if there is evapotranspiration, then I could use a evapotranspiration coefficient factor to correct my delta 18O values of the end member and then after apply it. So, even if there is a slight change due to any kind of physical process related fractionation, then also I will be able to do the conservative mixing model by applying a known correction. Okay. Main thing is that it is chemically and biologically inert, because if there is chemical interaction and biological interaction, it can have immense possibilities. It can be extremely difficult to be able to calculate that with precision. So, therefore, what we can rather do is use physical corrections related to evapotranspiration or temperature related corrections, taking weighted means and all that. That will basically correct any kind of small physical process related corrections. Otherwise, 18O and delta D are extremely good conservative traces. That is why it is applied as the major tracer to to do source apportionment of water. With this, I come to the end of this lecture. We will be discussing more about how to do source apportionment with delta 18O and delta D values in our next lecture. Thank you.